Good evening, my YouTube viewers. It is Crystal here, and I'm just here this evening because I wanted to make a video to discuss sampling distributions with you, and we're going to discuss the sampling distributions using the R programming language. And so we're going to be covering several sampling distributions in this video. So the first sampling distribution that we're going to talk about is the distribution of the sample mean. And what the sampling distribution of the sample mean does is it proves the central limit theorem. So the central limit theorem states that it doesn't matter what kind of distribution you have, if your samples in that distribution, if the distribution is sufficiently large and you have number of samples in that distribution are sufficiently large, then the samples themselves will create a normal distribution. And so that's what we're going to discuss in this particular cell. So the first thing that we want to do is we want to set our seed, because what happens when you set the seed is every time you run the cell, then the seed is going to be initialize the variables to the same values. So you set dot seed brackets 1, 2, 3. And then we're going to create a non-normal distribution to make the CLT, that central limit theorem, effect visible. So we're going to use an exponential distribution that is skewed to the right. So population becomes Rx, that's a randomly placed exponential distribution, brackets 100,000, comma, rate equals 1 divided by 10, brackets. And so that gives you a mean of 10 that's right skewed. N is your sample size. It's going to be 30. Number of samples is 5,000. And then sample means becomes replicate, brackets, num samples, comma, curly brackets, mean, brackets, sample, brackets, population, comma, n, comma, replace equal true, brackets. And so basically what we're going to do is we're going to be sampling with replacement. So if you notice, if you remember in my last video or the last couple of videos, we were talking about different types of sampling. So you can have sample with replacement and sample without replacement. So when you have sample with replacement, every time you sample a vector, it's going to put that value back into the vector. But sample without replacement is every time you sample a vector, then it doesn't go back, that value doesn't go back into the vector. And then so we're going to create a histogram of our vector of sample means. So hist bracket sample means, comma, breaks equals 40, comma, color equals sky blue, comma, border equals white, comma, main, that's your title, sampling distributions of the sample mean, comma, xlab, that's your label on your x-axis, equals sample mean. Then we're going to add a vertical line at the population mean. So AB line, brackets, V equals mean, brackets, population, comma, color equals red, comma, line width equals 2. And then so when we run this cell, what we're going to do is we're going to get a histogram, the sampling distribution of the sample mean. And this histogram is going to be really close to a normal distribution, which is a bell curve. So like the more samples that you have, the more like a normal distribution the distribution of the sample means will be. And so this proves the central limit theorem. So the next thing we're going to do is we're going to sample distribution of the sample proportion. And so the first thing we want to do is we want to define the population proportion. And so we're going to set our seed. So every time we run this cell, the values are the variables are going to initialize to the same values. So you type set.seed brackets 1, 2, 3. P true is your true population proportion, and it's .4. And then we're going to draw repeated samples and compute sample proportions. Your sample size is 50. Your number of samples is 5,000. So sample props becomes replicate brackets num samples, comma, curly brackets, mean brackets, R binomial brackets, n, comma, size equals 1, comma, prob equals P true brackets. So what we're going to do in this regard is we're going to create a binomial distribution, and we're going to randomly select the values from the binomial distribution. And so we're going to call that sample props. And we're going to plot your sampling distribution. So we're going to create a histogram. So hist bracket sample props, comma, breaks equals 30, comma, color equals light green, comma, border equals white, comma, main equals sampling distribution of the sample proportion. So that's your title, and xlab is your x label is a sample proportion. And then we're going to add a vertical line at the true population proportion. So AB line brackets V equals P true, comma, color equals red, comma, line width equals 2. So when we run that cell, we get the sampling distribution of the sample proportion. And so your nominal sample proportion is 0.4, and the values go all the way from 0.2 to 0.6. And that's going to give you also a normal, the samples are going to give you a normal distribution or something resembling a normal distribution, even though the we've created a binomial distribution. So the next thing we want to do is we want to talk about the chi-square distribution. It's used in test of independence and goodness of fit test. It describes the distribution of the sum of squared standard normal variables, and we're going to simulate chi-square values. So we're going to set our seed, and what that does is every time you run the cell, the variables are going to set up to the same values. So set.seed brackets 1, 2, 3. And your degree of freedom is going to be 6. And so the thing is that you can set the degree of freedom to any value that you want. And the value of the degrees of freedom are going to determine the size, the shape of the distribution. So you can experiment with the degree of freedom to make like small degrees of freedom and large degrees of freedom, so you can see what the distribution looks like based upon the degree of freedom. And then so chi-vals becomes R chi-square brackets n, comma, df equals df. So R chi-square means you're going to be creating a chi-square, a randomly selected chi-square distribution, and n is your number of simulated values, and df is your degrees of freedom. So we're going to plot the distribution into a histogram. So hist brackets chi-vals, comma, break equals 40, comma, color equals light blue, comma, border equals white, comma, frequency equals false. And what this does is this makes the density curve visible, because we're also going to put a density curve in there. Main equals paste, brackets, chi-square distribution, brackets, df equals df, brackets. Okay, so what you're doing in this instance, so you're not printing, and the reason, because you're going to be inputting data into the title. So, and you're also not using cat, so you use paste to paste data actually into the title. And xlab is your label for your x-axis is values. And now we're going to create our density curve. So curve brackets d chi-square brackets x comma df equals df. So df is your degree of freedom, comma from equals 0, comma 2 equals max brackets chi-square vowels, comma add equals true, comma color equals red, comma line width equals 2. So we're going to create our chi-square distribution with a degree of freedom of 6. So you can see that the shape of this chi-square distribution. But if you change the degree of freedoms to a lesser value or a higher value, that's going to change the shape of your distribution. So you're probably going to want to experiment with that and see how the distribution changes as you change the degree of freedom. So the next distribution we have is the t distribution, which is used when estimating population parameters when the sample size is small and or the population standard deviation isn't known. Okay, so the t distribution is similar to a normal distribution, except for the fact that its tails are fatter. So the first thing we're going to do is we're going to create the values for the t distribution. We're going to set the seed so that every time we run this cell, the variables are going to be set up to the same values. So set.seed brackets 1, 2, 3. And the degree of freedom is 20. And you can set the degree of freedom up to any value that you want. And what will happen is the values of the degree of freedom that you set will affect the shape of the distribution. So you're probably going to want to experiment with this and change the values of the degree of freedom so you can see how the shape of the distribution changes. Your number of simulated values is 5,000. So t-vals becomes RT brackets n, comma, df equals df. So RT means randomly selected t distribution. N is 5,000, your number of simulated values, and df is 20. So now we're going to plot the distribution. So dist brackets t-vals, comma, breaks equals 40, comma, color equals light blue, comma, border equals white, comma, frequency equals false, comma, main equals paste, brackets, t distribution, brackets, df equals df, brackets. And so basically what you're doing is you're inputting a value into the title of the chart. X lab, that's your X label. And then so now what we're going to do is we're going to add a density curve into the chart. So curve, brackets, dt, so that's a t distribution, brackets x, comma, df equals df, comma, from equals minimum brackets t-vals, comma, 2 equals max t-vals, comma, add equals true, color equals red, line width equals 2. And then so we run that cell, and you have a t distribution with a degree of freedom of 20, and you can see that it looks similar to a normal distribution. But the main difference between a t distribution and a normal distribution is the fact that the tails in the t distribution are fatter than the tails in the normal distribution. So that's one thing to keep in mind. So now, in the last video, the last cell, we were talking about the t distribution. So what we're going to do is we're going to compare a t distribution to a normal distribution so you can see the difference for yourself. So df becomes 5, and then we're going to create a curve, brackets dt, that's a t distribution, brackets x, comma, df equals df, brackets, comma, from -4, to 4, color equals blue, line width equals 2, y lab, that's your label on your y-axis, equals density, main equals paste, brackets, t versus normal, brackets, df equals df, brackets. And then so basically what you're doing is you use this paste command because you're actually pasting information into the label of the chart. And so now we're going to create another curve of the normal distribution. So curve, brackets, d norm, brackets, x, add equals true, color equals red, line width equals 2, LTY equals 2. So you notice that the t distribution is blue and the normal distribution is red. So we're going to have a legend, which is on the top right, and it's going to say t distribution and normal. And the colors are going to be blue and red. The line width is 2, and the LTY is 1, 2. So when we run that cell, so you can see you've got your t distribution versus the normal distribution with degree of freedom of 5. And so our normal distribution is red, and the t distribution is blue. So you can see that the normal distribution is very close to the t distribution, with the exception that the tails are fatter in the t distribution than they are the normal distribution. So now we're going to talk about the F distribution. So F distribution is the distribution of the ratio of two independent chi-square variables divided by the respective degrees of freedom. So the first thing that we're going to do is we're going to generate the values, and we want to set our seed. So every time we run the cell, the variables are going to be set up to the initialized to the same values. So set.seed brackets 1, 2, 3. We're going to set df1 equals 5, and that's the numerator degrees of freedom, and df2 becomes 50, and that's the denominator degrees of freedom, and becomes 5,000, that's the number of simulated values. So f vals becomes RF, so that's randomly selective F distribution, brackets N, that's your simulated values, df1 equals df1, df2 equals df2, and then we're going to plot the distribution into a histogram. So hist brackets F vals, breaks equals 40, color equals light golden rod, border equals white, frequency equals false, main equals paste, brackets F distribution, brackets df1 equals df1, df2 equals df2, brackets. And so what that does is that pastes the df1 and df2 into the actual title, and xlab is the label of your x-axis, and then we're going to add a density curve to the chart. So curve brackets df brackets x, df1 equals df1, df2 equals df2, from equals 0, 2 equals max, brackets f vals, add equals true, color equals red, line width equals 2. So when we run the cell, so you can see that we've got our F distribution with a numerator degree of freedom of 5 and the denominator degree of freedom of 50. And so if you change the degrees of freedom, so the numerator and the denominator, that is going to actually change the shape of your distribution. So you're probably going to want to experiment with the degrees of freedom for the numerator and the denominator so you can see how the shape of your distribution changes. The next thing we have is a binomial distribution that describes the distribution of the number of successes in a fixed number of independent Bernoulli trials with the same probability of success. So we're going to replicate this, and the first thing that we're going to do is we're going to define our parameters. N becomes 20, which is your number of trials, and P becomes 0.3, which is your probability of success. And so now we're going to compute the probability mass function, which is also your PMF. So X becomes 0 to N, so 0 to 20 really. PMF becomes D binom, brackets X, comma, size equals N, comma, prob equals P. So basically what we're doing is we're creating a binomial distribution to do this, to plot this graph. So then we're going to plot the distribution. So plot brackets X, comma, PMF, comma, type equals H, comma, line width equals 3, comma, color equals steel blue, comma, main equals paste, brackets, binomial distribution, brackets N equals N, comma, P equals P, brackets. And so basically what you're doing is you're pasting data into the title of the chart. X-lab is the label of your x-axis, which is number of success. Y-lab is the label of the y-axis, which is probability. So points, brackets, X, comma, PMF, comma, PCH equals 16, comma, color equals teal blue. And then so we're going to create this binomial distribution with N equals 20. That's number of tests, and probability equals 0.3. So this is your number of successes, and your probability is 3. So that's telling you that at number 6, if you have number 6 is you're going to be your highest probability of success, and anything after 11 is going to be your lowest probability of success. So the next thing we're going to do is we're going to simulate a binomial distribution. So we're going to do that by setting our seed. So every time we run this cell, the variables are going to be initialized to the same values. So set.seed brackets 1, 2, 3, sim vals, that simulated values, becomes R binom brackets 5,000, comma, size equals N, comma, probability equals N. So R binom is a binomial distribution that's randomly selected, and N is your number of trials, and probability, and P is your probability of success. So we'll just put a little note in here. And then we're going to create a histogram of the simulated binomial distribution. So hist bracket sim vals, comma, breaks equals SEQ bracket 0.5, comma, N plus 0.5, comma, 1. So negative 0.5 is going to be the smallest point, and N plus 0.5 is going to be your largest point. And I think we said N before is 20. N, you've got N. So we're going to say here and probability equals, okay, and then so our main is simulated binomial distribution, and X lab, that's your label for your x-axis, is number of successes. So we're going to simulate our binomial distribution. So you've got 20 trials. The highest probability I think is going to be number 6. If you have 6 trials, you're going to have, that's going to be the highest success. Anything below 11 or 12 is going to be your lowest success. So that's very similar to the distribution that we covered previously, but it's just telling you how to do it. And the reason why is because we use the same n value and the same p value. If we changed our n and changed our p, the binomial distribution would have a different shape. So the next thing that we have is the Poisson distribution, which describes the distribution of the number of events occurring in a fixed interval of time or space, given a constant mean rate of occurrence. So what we're going to do is we're going to create a Poisson distribution, and we're going to define the Poisson parameter. So the first thing that you want to do is you want to have lambda becomes 4. So your lambda is the value that we're going to use to define the shape of the distribution. And so we're going to compute the probability mass function, that's PMF. X becomes 0 to 15. PMF becomes D poise. That's a Poisson distribution, brackets X, comma, lambda equals lambda. Plot the, and then we're going to plot the distribution. So plot brackets X, comma, PMF, that's your probability mass function, comma, type equals H, comma, line width equals 3, comma, color equals dark orange, comma, main equals pace, Poisson distribution, lambda equals lambda. And so basically what you're going to do is you're going to paste the value of lambda into the title of the graph. X lab is the label on the x-axis, which is count, and Y lab is the label of the y-axis, which is probability. And then we're also going to set some points, brackets X, comma, PMF, comma, PCH equals 16, comma, color equals dark orange. So when we run the program, when we run the cell, this is your Poisson distribution with a lambda of 4. And so basically what's going to happen, you can experiment with the values of lambda, because the different values of lambda are going to change the shape of the Poisson distribution. So you can use different values of lambda and experiment with that to see what happens. So now what we're going to do is we're going to sample distribution of the sample variance, and we're going to create a population. To do that, we're going to set our seed, because we need to set our seed so every time you run the cell, you want the variables to be set up to the same values. So set.seed brackets 1, 2, 3. Then we're going to create the population, becomes R norm. So that's going to be a randomly selected normal distribution, brackets 100,000, comma, mean equals 50, comma, SD, that's your standard deviation, equals 10 brackets. And then we're going to draw repeated samples and compute sample variances. So N becomes 30, and your num samples becomes 5,000, and your sample vars becomes replicate, brackets, num samples, comma, curly brackets, var, comma, sample brackets, population, comma, N, comma, replace equals true. So this is sampling. We're going to be utilizing sampling with replacement in this instance. And then we're going to plot the sampling distribution. So we're going to make a histogram with that. So hist bracket sample theirs, comma, breaks equals 40, comma, color equals sky blue, comma, border equals white, comma, main equals sampling distribution of the sample variance. And so that's your title. XLab is your label for your x-axis, which is your sample variance. So you can see we've also checked the sample variance, and the sample variance resembles a normal distribution, but it is also just a little bit right skewed. But what I wanted to check here, so n is 30. I just wanted to check something. So n is your number of trials. N is your number. So that actually concludes this video, because we've covered all of the distributions that I wanted to put in this video, and there's lots more distributions. There's lots of distributions that you can cover in statistics, but the only distributions that I've covered in this video are the ones that I've covered. But you can also do a search on the internet and just ask the question, how many distributions are in the R programming language? And then it will give you a list of all the distributions in the R programming language, and then you can experiment with making them as well. So that concludes this video. The next video is going to be on another statistical subject in R, and so I hope that you decide to watch it.